Okay, I'm a little bit slow on this starting, but nonetheless, so we looked at this. This is the ocean acidification story, that increasing CO2 in the atmosphere is going to dissolve more CO2 into the ocean, which is going to drive consumption of carbonate ion, which is going to come from splitting calcium carbonate and reduce the saturation of or make the calcium carbonate be less than saturated in surface waters, which is going to drive dissolution of carbonate shell forming species like corals. So conservative quantity is then the total CO2. So that is written obviously as CO2 concentration plus carbonic acid plus bicarbonate and carbonate. So this is not going to change by moving things around or mixing different water masses. This is a conservative quantity, and models can easily carry this. Then there is the concept of alkalinity. We talked about H plus being released from dissolution of CO2 into seawater, and what is alkalinity is basically the base needed to neutralize the acid that is present by creating H plus. So it's not just calcium carbonate. So there are other salts in the ocean like boron, borate, whatever it's called, phosphate, silica, and so on. So this is a figure from this site here. So atmospheric CO2 dissolves, gives us H2CO3. Then you have bicarbonate, and then alkalinity is what determines how much base is needed. So it's like a pH titration where you keep adding base till you neutralize the solution and all the CO2 escapes as gas. That's what is the total alkalinity, and that is a conservative quantity to mixing and so on, advection as well. So in the model it's very easy to carry that. So alkalinity, carbonate alkalinity is just the carbonate and bicarbonate ions, because it has two negative charges. You have two times, so it's the total number of negative signs which are needed, which are going to neutralize the H plus, right? So you can add the equations we have seen before of the carbon CO2 dissolution. So CO2 plus carbonate plus H2O is going to give us 2HCO3 minus. So this equation is a bit weird because it has negative ions on both sides. CO2 can escape out of the water, but these salts cannot. So by moving this reaction around, we are not going to change the alkalinity. So alkalinity is a conservative quantity. That's the main message of how alkalinity and carbon chemistry work. You have carbonate chemistry, which is very critical, which obviously is very closely related to what we are worried about in terms of not just how warm the ocean is getting, right? That's a direct effect of increasing the amount of energy trapped in the atmosphere because of increasing greenhouse gases. More than 90% of that, almost 93% of it, goes into the ocean. Rapid warming of the ocean has all sorts of consequences for living things in the ocean, as well as the stratification changes, carbon source sink of the ocean over time, mixing up of nutrients, primary production, and so on. But there is the direct consequence of increasing CO2 in the atmosphere, which is to drive acidification. And we are not talking necessarily about pH change. We are talking about consumption of the carbonate ion because of this reaction. The more you increase CO2, the more carbonate ions are going to be taken down, and they're going to come from calcium carbonate. So to look at it a little bit more detail, this is another cartoon showing the same thing. CO2 gaseous form becoming hydrated in aqueous form, dissolved hydrated form H2CO3 splitting into bicarbonate and then carbonate, and then there is plenty of calcium in the ocean. Calcium is not in deficit. It's constantly getting washed into the ocean. It's the carbonate ion that is going to be used up by increasing H plus and CO2. That's the main concern here. Okay, and this is the pH reaction we saw before. 7 is of course the distilled water, which is pure. Then you have acidic things that are less than 7, like milk, black tea, black coffee, tomato juice, lemon juice, and so on. And you have basic things, alkaline things on this side, fresh egg white, laundry detergent, ammonia liquid, and so on. So you can think of calcium carbonate here as Pepto-Bismol, right, which is neutralizing acid, but as you keep increasing CO2, that's going to be a problem. So there are differences in the consumption of carbonate ions and so on, and we have seen this figure before. As we keep increasing CO2, you can see CO2 is increasing in this direction. The CO3, carbonate ion is going to drop rapidly, and H plus is increasing rapidly as well, which is what gives us the reduction in pH. And then there is the bicarbonate that is got a different rate of change. You can see here this is rapidly increasing, rapidly dropping, but this is balancing. That's the basic buffering of CO2. Why CO2 is much more than bicarbonate in the ocean and why carbonate is much more than CO2 is because of these reactions that buffer the CO2 dissolution in the water. We saw this in another form where we said if we look at the atmospheric CO2 over time, the glacial CO2 change and the pH change in the ocean. Ocean has maintained its pH at this level for a long time, but the projection is that as we continue to increase CO2, right, we're already on this trajectory, pH is going to drop to levels not seen for a very long time. Okay, this is an example of how nonlinear these things are. So this is from PMEL here, showing at the pre-industrial CO2 level of 280, H2CO3 carbonic acid was 8 units. The HCO3 minus was 16, 17, and carbonate, so bicarbonate and carbonate, 268. But as you double CO2 or triple CO2, this is not a linear change. Carbonic acid goes to 15 and then 26, so progressively less. And then bicarbonate increases as you expect, but progressively less rapidly. And then bicarbonate begins to drop off. This is our main issue with ocean acidification, that CO2 increase in the atmosphere is going to begin to draw down carbonate ions, and you can see that DIC changes are shown here from 1893 to 2040 and 2155, and the pH drops. So these are the nonlinearities which are the buffering of CO2 in the ocean, but it comes with the consequence. This is thus dissolved inorganic carbon, not the total CO2. So you have to do TOC and not DIC to get the conservative quantity that we talked about. So with that background, we'll move to biological pump as one of the explanations for glacial drawdown, ice age drawdown of CO2, or another way to say it, the glacial release of CO2. Can the ocean biology have done it? We will see that that also doesn't really work when we take all matters into consideration, including the isotopic signatures. Okay.